To illustrate this topic, we will use a problem that is described on page 2 of the textbook. A large department store is having a 4th of July sale, which actually starts on July 2nd. And the plan is to send out an 8-page advertisement at least 10 days before July 2nd in order to be effective. Now, several tasks must be done and decisions must be made. As you can see in this chart, some of the tasks can be done simultaneously. However, many tasks cannot even be started until others are completed. As you can see here, the first task, for example, the department managers will choose items that are in stock for this sale, and the buyers will choose items that need to be brought in for sale. So these two tasks can be done simultaneously. Now, the team that is in charge of task number 3, to choose items and price the items for the ad, cannot start the task until these two first are completed. Now, labeling the tasks and indicating the preceding tasks, then we will have a chart that will help us figure out the shortest time to complete this project. Now we can use the labels to identify the preceding tasks. Task A, for example, doesn't have any preceding task, so we will just write none here. Same thing with task B. Task C cannot be started until A and B are completed, and that will take at least 3 days. So we'll just identify the preceding tasks here, A and B. Task D cannot be started until task C is completed. Task E can also be started simultaneously with task D, but only after C is completed. Now, to design the advertisement, that cannot be started until D and E are completed. Compiling mailing list, so that can be started after C is completed. And then printing the labels cannot start until all the other ones are completed. So we'll put G here. This requires task F to be completed, and this one, H and I. And finally, the last task, to deliver the advertisement, can start only after J is completed. The information provided in the table can be more easily understood if it's presented in a graphical format. We're going to make use of a mathematical object called graph. Now, this is not graph that you have probably seen in college algebra or some other math courses. Graph here is made of points and segments. The points here are the tasks, and the segments represent relationship between two tasks. For example, here we're going to draw this segment with an arrow indicating that the point A precedes point C. So in our problem, then A here is a preceding task to C. So this is how we can start a graph for this problem. Now we can also use circles to represent these tasks. And we're going to make an assumption here that we're going to read the graph from left to right. This way we're not going to need the arrowheads. So this is how we model the problem. Task A and B, they don't have any preceding tasks. And then here's task C. And since A and B are preceding tasks to C, we're going to use a segment. And we don't need the arrowhead in this case, since we're reading from left to right. Here's task D. Notice that task F cannot be completed, cannot be started until D and E are completed. So this will show how long each task takes. Task A, for example, takes 3 days, task B takes 2 days, and so forth. Now, using this graphical format, then we can easily calculate the least amount of time to complete the entire project. Beside each letter of the graph, beside each label of the graph, we're going to write a number that represents the total time of the project from the beginning up to that specific point, up to that specific task. For example, here for task A, we're going to write 3, which means that from the beginning up to the completion of task A, we'll have a total of 3 days. And then same thing here, from the beginning up to the completion of task B, it will take 2 days. Notice that these two tasks are independent, so they don't have any preceding tasks. Then, however, to begin task C, we'll have to wait at least 3 days. So the total time from the beginning of the project up to the completion of task C, it will be 5. And that's because we'll choose the maximum number here between 2 and 3 and add to 2, and that gives us 5. And then we'll do that for each label. So for example here, task F, from the beginning of the project up to the completion of task F, we'll have 11 days. And the reason is that we cannot start task F until 9 days have passed. So even though the completion of task E, from the beginning to the end of task E, that will take 8 days, we'll still need to wait 1 more day so that D can be finished. And then we can start task F. So the total project time from the beginning up to the end of task F is 11. And we keep doing that for all the other labels. So notice that this is the very last task, and that gives us the total time to complete the entire project. This method that we just described is called the PERT method, which stands for Program Evaluation and Review Technique. The PERT method was created in the 1950s by the U.S. Navy. And as a solution for our problem, we can say that the advertisement can be produced and delivered in 28 days. Now, this graph also can give us extra information. Here we define the critical path, which is a path containing the tasks that determine the total project time. If we want to make any improvement, let's say, for example, we want to improve from 28 days to 27 days. So, for example, we can either improve task K from 10 to 9, or we can improve some of these previous tasks. Now, notice that task J depends on H and I. Even if I improve this number here, 9, let's say, for example, to 8, that doesn't change the number 18 in here, because the maximum here is what we take in consideration to add to 2, and that will give us 18. So notice that H doesn't have much importance here. Here, for example, even if in task G, even if I improve that, if we can improve that from 3 to 2 days, for example, then this would have been 7, and this would be 8, but the 18 here would still be the same, because that really depends on the maximum number. So identifying the important tasks, the critical tasks, which will define the critical path, those are the tasks that if you make any improvement on them in regards to time, then that will affect the total project time. So you can work backwards and then pick the labels that have the highest numbers. So from K to J, we pick 18. That's the J is the only task preceding K. Now from J we look backwards and we see 9 and 16, so we pick 16 and that gives us task I. We look backwards, pick F. We look backwards, we see E and D, but we're going to pick the highest, which is 9, so that will give us D. Until we reach the beginning of the project. And this is the critical path.